Hello, my name is Shengyao. You can call me Arvin. I'm a PhD student from the University of Queensland. This talk is about my ECIR 2020 paper, Counterfactual Online Learning to Rank. This is a joint work with my supervisor, Zhuang. First, I want to cover a little bit background of online learning to rank. So traditional offline learning to rank method requires human label dataset as its training signal. It has been proved that offline learning to rank is very effective. In fact, most of modern search engines have used offline learning to rank to improve their performance. However, the offline method has some obvious drawbacks. For example, training sets are always very expensive to collect, and there is privacy issues such as labeling user emails is not allowed. Apart from labels, there is another type of learning signal, implicit user feedbacks. So one of the most typical implicit feedback is click. The idea of online learning to rank is we want to interactively optimize our ranking system based only on these user feedbacks. The advantage is that there is no human labeling effort anymore because these clicks is countless generated by user every day and they can be easily logged. However, the drawback is also significant. So the biggest drawback is that clicks are highly biased learning signal. One of the well-known biases is this so-called position bias, which says the probability of a document being clicked depends not only on its relevance, but also on its position in the result page. This is because people tend to pay more attention on the top-ranked document, which means this document have more chance to be observed by the user, so that more likely to be clicked, even they are not relevant. So you have to keep this bias in mind if you want to use clicks as your training signal. So the traditional online learning to rank method can deal with user clicks. These methods are based on online evaluation, while interleaving or multi-leaving comparison is used to infer which rank is better. There is an example of interleaving. So basically, you have a current ranker and a candidate ranker. You use both rankers to generate two different result lists, and then you combine the two based on the interleaving rules, and then you show the combined list to the user. This interleaving online evaluation can tell you which ranker is better based on the user clicks. If your candidate ranker is better, you just update your current ranker a tiny step to the candidate ranker. This interleaving can be extended to multi-leaving method, which allows you to evaluate multiple rankers within one user interaction. So the state-of-the-art online learning to rank algorithm is this PDGD method, pairwise differentiable gradient descent. One thing I want to say here is that this method does not rely on online evaluation. Instead, it estimates its gradient using inferred pairwise document performance. So it is completely different algorithm. In addition to the online evaluation, there is another type of method that can deal with user clicks, which is this counterfactual evaluation or counterfactual learning. This type of method can unbiasedly evaluate a new system or new policy from data collected by an old system. This method treats rankers as a policies that can sample documents from a probability distribution to create a result list, and then use this inverse propensity scoring with this important sampling trick to fix the distribution mismatch between the new and the old ranker. This is saying that you can directly compare two rankers even though the learning signal is collected from different probability distribution. So you can think of this IPI score of the new ranker is the average cumulative rewards received by the old ranker, but reweighted by the important sampling term. So the delta here is the reward received by your old ranker and the times the important sampling term. In fact, if you do the math here, you can find the IPS score is an unbiased estimator. So I guess the motivation of our work is that can we replace traditional online evaluation with counterfactual evaluation, for online learning to rank? Because both methods kind of doing the same thing. They both are used to evaluate which ranker is better given user clicks. So we want to investigate if the counterfactual can gain more benefits than online evaluation. Now I'm going to explain all the steps of our design algorithm, the counterfactual online learning to rank. So when the user input a query to the search engine, generally the search engine has a candidate document collection associated with the query. And we use our current ranker to compute document score and then perform a softmax on them to get a probability distribution so that we can sample document to get a result page. Then we show the result page to the user. The user will make some clicks on it, and we following counterfactual risk minimization framework, we assign reward 0 to document that the user clicked on or user did not observe, and assign reward 1 to the document that the user observed but did not click. You can think of this CRM is what we want to penalty the document the user observed but did not click. It is saying that those documents are risks if you put them in the result page. So we want to minimize this risk. So by the way, we made an assumption that the user always examines document from top to bottom and abandon the search engine after the last click. So we can guarantee that the document above the last click have been observed by the user, and document below the last click are not. In fact, this assumption is a very common in online learning to rank tasks. So now we have user click feedbacks, and next, same as interleaving or multi-leaving method, we randomly generate some candidate rankers by shifting the parameter of the current ranker on its unit sphere in the parameter space. And we do the softmax again for all the candidate rankers so that we can have the probability distribution to compute the IPS score of each candidate rankers. Now, the winner rankers are those IPS scores smaller than that of the current ranker, because smaller now indicate that those rankers have lower risk. And we update our current ranker a tiny step towards to the mean of the winner rankers. So for experiment detail, we compiled our method with 3 baselines. So the probability interleaving gradient descent and the probabilistic multi-leaving gradient descent, which are both using online evaluation, and also the state-of-the-art method PDGD that I mentioned before. And we test our method and the baselines on 4 commonly used learning to rank dataset. So the MQ 2007, 2008, they're bit small and old dataset, and MLSR10K and Yahoo, which are bigger and more recent dataset. Like other online learning to rank experiments, we not test our method with real world users. Instead, we simulate user clicks behavior based on click model. And here we have 3 different click models: perfect click model, navigational click model, and informational click model. So the perfect click model that simulate user will not click on irrelevant documents and will observe every document in the result page. So there's no click noise and no position bias at all. And for the navigational and informational click models, which will give different level of noise, clicks, and position bias. Again, this is a standard experimental setting for online learning to rank. So for evaluation matrix, we use offline performance, which is the NDCG score of the learned ranker on the test set. This metric is basically same as other IL tasks. We also care about user experience during the training, which we evaluate by this online performance metric. So this online performance is the cumulative NDCG scores of the displayed result pages that the user observed during the training, but weighted by the discount factor gamma. So this gamma usually is a number bit smaller than 1, so it weighs more on recent result page and less for later ones. Again, this online performance can evaluate user experience. So for the result, the first research question we want to answer here is, how does the number of candidate rankers influence the offline performance of our method? We conduct these experiments on the noise click model, so this informational click model, and we simulate 10,000 user interactions. We first tested when the number of candidates equals 1, which we aim to compare with the interleaving baseline, so this PIGD. So remember, the interleaving method also compare only 1 candidate ranker for each update. So the purple line at the bottom is our method, and the black line is the interleaving baseline. As you can see, our method is actually worse than the interleaving baseline. However, when we increase in the number of candidates to 49, the performance of our method significantly improved. So the yellow line is our method with the number of 49 candidates, and the light blue line is the multi-leaving baseline, whose number is also 49. So our method is significantly better than the multi-leaving and interleaving baseline. Then we tested larger number of candidates from 99 up to 999. We find that we can always get benefit by increasing the number of, our method can even outperform the state of the art, which is the blue line in the middle. Then the number, but the performance plateaued after 499. So we keep the number to 499 for the rest of our experiments. Another thing I want to mention here is that the reason we only do the 49 candidate for multi-leaving baseline is because the computational cost of online evaluation becomes considerable after this point. But for our method, counterfactual method does not rely on online evaluation. Instead, we just compute IPS score for each candidate rankers. So the computational cost is actually linear to the number of candidates for our method. As the result, we can easily compare huge number of candidate rankers. Our second research question is that what is the long-term performance of our method? So to investigate this, we're increasing the number of user interactions to 100,000. We find that the multi-leaving method performs much better with more user interactions, but still worse than the state of the art and our method with 499 candidate rankers. Then our third research question is how different click model influenced offline performance. So we did the same experiments on 3 different click models. We find that our method can always outperform the online evaluation baselines and match the state of the art, except for the perfect click model. So the top figure is the result for perfect click model. Our method is actually a bit worse than the state of the art, but still better than the online evaluation baseline. Finally, our last research question is that what is user experience for our method? So the online performance. Our method is actually not doing so well. It is always better than the interleaving baseline, but for multi-leaving and state of the art, it is always worse. So I guess the reason for this is because our counterfactual method is using softmax to sampling document from the collection. So there is a chance that you sample a very bad document into the result list, which will hurt the user experience. In fact, you can make the softmax more deterministic by decreasing the temperature parameter tau of the function, and this will give you less chance to sample a bad document, so that can increase in the online performance. But on the other hand, it will hurt offline performance. So there is a classic exploration and exploitation trade-off. To conclude our work, we introduced a novel online learning to rank algorithm, counterfactual online learning to rank. Our method replaces the traditional online evaluation with counterfactual evaluation. By doing this, we can enjoy much better offline performance and a much better computational efficiency than the online evaluation. However, our method still has lots of room for improvement of the user experience. For future works, we want to investigate more about how to balance exploration and the exploitation trade-off. To get good result for both online and offline performance. Then also, we are also considering to extend our work to reuse historical click data to have more reliable counterfactual evaluation. So you can find the experiment code in my GitHub repository. For more information about the paper, please visit our IE Lab website. Thank you for listening.